Chapter 15, Quantum Translation, Section 15.3, Heisenberg's Uncertainty Principle. The wave function of the particle in the one-dimensional box is the square root of 2 over a times sine n pi x over a. A is the box length, n is the quantum number. The uncertainty of the position of the particle is approximately 1/2 of the dimension of the box, just because the position is within a range of 1/2 of a plus minus 1/2 of a. So really, this is a range from 0 to a. The uncertainty of the momentum of the particle is n pi over a times h bar, because the momentum of the particle is plus minus n pi over a times h bar. N is the quantum number 1, 2, 3, 4, etc. And therefore, we can have the product of the uncertainty of the position and the uncertainty of the momentum. The product is 1/2 of a times n pi over a times h bar. And we have n pi h bar over 2, or this, since this n is 1 or 2 or 3 or 4, the minimum value for n is 1. Therefore, the product of the uncertainties is greater than or equal to pi h bar over 2. And therefore, the Heisenberg's uncertainty principle holds, which states that the uncertainty of the position times the uncertainty of the momentum of the same particle must be greater than or equal to 1/2 of h bar, and certainly pi over 2 is greater than 1/2. The uncertainty of the position can also be determined more accurately using this equation for the standard deviation. The standard deviation of x can be computed this way: the square root of the average of x squared minus the squared average. Postulate 4 can be used to calculate the expectation values and also the standard deviation of the physical properties of the particle in the box, such as position. Now, given this wave function, we can compute the average value for x. It's pretty simple. It's the integral of psi star and then x operator applied to psi dx. X is from 0 to a, because outside the box the probability is 0. We just need to integrate this. To integrate this, we need to solve this integral, which is non-trivial. So I used Wolfram alpha to integrate this whole thing. I got 1/2 of a as the expectation value for the position of the particle in the box. And also, we can avoid doing any mathematics. We just look at the shape of the wave function. Well, it's fairly symmetrical, and work as, this x would have the average at the midpoint of the box. Now let's look at the average of x squared. So again, we'll just integrate this. We integrate the this is the psi star, the complex conjugate of the wave function, and then the operator is x squared applied to psi. So integrate this. I used Wolfram alpha again. I got a squared over 3. This is really non-trivial calculation. Now, since we have the average of x and the average of x squared, we can calculate the standard deviation. Delta x is the square root of the average of x squared and the average of x and then squared. So we plug in the expressions, we get 0.29a. So this is the standard deviation of the position of the particle in the box. and this value does not depend on the quantum number n. So no matter n is 1 or 2 or 3 or 4, well, the standard deviation of the position is always 0.29a. Postulate 4 can also be used to calculate the expectation value and the standard deviation of the momentum of the particle in the box. So now let's look at the average momentum. We know it should be 0 because if we look at the wave function of the particle in the box, it's either sine n pi x over a or simply sine kx, where k is n pi over a. So either way, the sine function can be expressed as a linear combination of two exponential functions. One is e to the power of ikx with a momentum of kh bar. The other exponential function is e to the power of negative ikx with a negative momentum, which is negative kh bar. So this particle may have a momentum of kh bar or negative kh bar with 50-50 chance. Therefore, we know its average momentum should be 0. But still, let's look at this integral. Again, we integrate this psi star, and we apply the momentum operator to the wave function psi. And now we evaluate this. This is actually pretty easy, only because dx and dx cancel. So really, we have a constant here, and then integral of a sine function multiplied by the differential of the sine function. Well, you can just use some variable substitution. So you can say, well, this sine n pi x over a is z, and then you just integrate z dz, which is going to be just 1/2 z squared. What's the limit of z? Well, you can just plug in 0 here, you get sine 0. You plug in a here, you get sine n pi. So sine 0 is 0. Sine n pi is also 0. So the lower limit and upper limit for z are both 0 if z is defined to be sine n pi x over a. Or you can just do this integral directly. Anyways, sine n pi a over a is 0. Sine n pi 0 over a is also 0. So this average of momentum of the particle in the box must be 0. Again, over here, this is just the trick to express a sine function as a linear combination of two exponential functions here with an equal weight. Alright, because the coefficients squared is proportional to the probability. So you have 1 squared versus negative 1 squared, they are the same. And their eigenvalues are kh bar and negative kh bar. Well, k is n pi over a. The probabilities are equal, so you have 50% chance to get n pi h bar over a, 50% chance to get negative n pi h bar over a. So the average has to be 0. Postulate 4 can also be used to compute the expectation value of the momentum squared of the particle in the box. Really, it's just the integral. This is psi star, the complex conjugate of the wave function. Here we have the operator, which is px squared, applied to the wave function. And we can simply do some mathematics. We evaluate this first. We apply px squared to the wave function, which is just the momentum operator applied to the wave function 2 times, and then we get this. Alright, and because this function is a normalized function, so we can simply just evaluate this integral to get the average of px squared. This is actually non-trivial, but I think we learned this. The momentum squared is actually 2 times the mass times the kinetic energy. Alright, and we know the kinetic energy is n squared h squared over 8ma squared. So this comes from the kinetic energy multiplied by 2m. Again, the kinetic energy is n squared h squared over 8ma squared, and then multiply by 2m, you get this expression. Or you can do the math. You can use Wolfram alpha, but also if you do know sine theta squared, you see this sine squared. If you know sine theta squared is 1 minus cosine 2 theta, and then divided by 2, you can still solve this integral easily. But anyway, we got this result over here. The standard deviation of the momentum is the square root of the average of momentum squared minus the average of the momentum and then squared. So this is just 0. We just plug in this here. We get nh over 2a. The standard deviation of delta px is nh over 2a. Now let's verify the Heisenberg uncertainty principle. We calculated delta x to be 0.29a. It's independent of the quantum number n. Delta px depends on the quantum number n. So it's nh over 2a. We do the multiplication. We get 0.88 nh. And this is okay. There's a typo over here. This is actually supposed to be h bar. Okay, so what I did is h is h bar times 2 pi. 2 pi over 2 is pi. And then pi times 0.29 is 0.88. So over here, this is actually 0.88 n h bar. And because the minimum value of n is 1, so this is greater than or equal to 0.88 h bar, which is greater than 1/2 h bar. And this delta x times delta px is proven to be greater than 1/2 h bar in accordance to Heisenberg's uncertainty principle. In general, if the operators of two physical properties, let's say A and B, do not commute, then the exact values of A and B cannot be determined simultaneously. So first, what does this mean, do not commute? Well, it simply means if we apply AB operator to a function and then apply BA operator to the same function, we get two different results. And that indicates AB is different from BA. Alright, if you are doing just multiplication of two numbers, AB equals BA always. However, if you are applying two operators to the same function, you might get a different result, which depends on the order, alright, of this two. For position and momentum, we can prove that their corresponding quantum mechanical operators do not commute, and therefore the exact values of position and momentum cannot be determined simultaneously. We can define the commutator of two operators to be this: A, B enclosed in a pair of square bracket, and this is defined to be AB minus BA. If the commutator of A and B is non-zero, that means AB is different from BA, then we cannot determine the exact values of A and B simultaneously. But what if the commutator of A and B is 0? Then that means, well, these two operators, A and B, they share one common set of eigenfunctions. And that means the exact values of A and B can be determined simultaneously. For example, the momentum operator over here and the kinetic energy operator over here, they do commute. So it's possible for us to determine the momentum and kinetic energy of the same system. So first, let's look at the commutator of the momentum operator and the kinetic energy operator. This is just notation. We have two operators inside, separated by a comma, enclosed by a pair of square brackets. We're about to apply this to an arbitrary function f. Really, it means, well, we're going to apply these two operators to f in a different order. Over here, kinetic energy operator first. Here, momentum operator first. And then kinetic energy operator. We'll take the difference. So over here, we just evaluate this. It's trivial. The result is I h bar cubed over 2m times the third derivative of f. What about this part? The same thing. Again, negative and negative cancel, and I goes here. H bar squared times h bar. We have h bar cubed. We have 2m on the bottom, 2m on the bottom, and really we're taking the second derivative of the first derivative. Well, which is simply the third derivative of f. So we have this two exactly the same, and then they cancel, we get 0. The kinetic energy operator and the momentum operator commute. Their commutator is 0. That means, well, they share a common set of eigenfunctions. For example, this function is an eigenfunction of the momentum operator and also the kinetic energy operator. E to the power of negative I kx is also an eigenfunction of the momentum operator and also the kinetic energy operator. Now it is possible to determine the momentum and kinetic energy of the same system exactly at the same time. For example, when we have a particle with this wave function, its momentum is exactly kh bar. Its kinetic energy is exactly k squared h bar squared over 2m. The position and momentum operators do not commute. So we can evaluate the commutator of the position operator and the momentum operator. So really, we'll just apply these two operators to function f in a different order. Here we apply x to f first, and then we apply momentum operator. On this side, we apply the momentum operator first, and then the position operator. So we have a common factor, negative I h bar. I take it here, and then we just need to evaluate d over dx of the product between x and fx. And here it's just minus x multiplied by f prime, the first derivative of f. So we need to use the product rule here. We get f plus x f prime, and then minus x f prime. In the end, we get negative I h bar times f. Again, when I say f prime, that's df over dx. F prime is simply a shorthand notation for the first derivative of f. Now, we can tell when we apply the commutator of the momentum operator and position operator to f, we didn't get 0. We get negative I h bar times fx. Alright, so that simply means the commutator of the momentum and position operators is equivalent to negative I h bar. When you apply this commutator to any function, it's equivalent to multiply this function by negative I h bar. So this commutator is equivalent to this operator. That means multiplied by negative I h bar. Now the physical meaning of the non-zero commutator of the position and momentum is that the position and momentum of a system can never be determined exactly and simultaneously, and that's the Heisenberg's uncertainty principle. We can never determine the position and momentum of the same system simultaneously. The uncertainty of position times the uncertainty of the momentum must be greater than or equal to 1/2 h bar. The Hamiltonian operator and the time operator do not commute either. So this is the commutator, it's non-zero. Now let's verify it. For an arbitrary function psi, we can write out the commutator applied to psi is equal to ht psi minus th psi. We just apply these two operators to psi in a different order. Postulate 5 can be expressed as a mathematical equation h psi equals ih bar delta psi over delta t. So really this h, this Hamiltonian, is ih bar delta over delta t. And therefore we have this expression converted to this expression. I replaced h with ih bar delta over delta t. And then this t operator is just multiplied by t. So when we do this, we need to use the product rule. The first derivative of t psi is psi plus t times psi prime. Over here we minus t times psi prime. ih bar is a common factor, so it's right here. And then we get ih bar times psi. Obviously, the commutator of the Hamiltonian and the time operator is equivalent to ih bar or multiplied by ih bar, and this is not zero. The physical meaning of this commutator of h and t being non-zero is that the total energy of a system cannot be determined exactly if the measurement is carried out within a finite time period. If you determine the energy within a finite time period, this delta t is finite, and then this delta E is also finite. The shorter the time period of the measurement, the larger the uncertainty of the energy measurement. We have an inequality expression similar to Heisenberg's uncertainty principle. Over here, delta E times delta T is also greater than or equal to 1/2 h bar. Delta T is the time period of the energy measurement. Delta E is the uncertainty of the energy measurement.